Welcome everybody to today's webinar. My name is Jill Browning and I'll be the moderator for today's webinar, Maximizing Water Recovery with CaptuRO, a resilient high recovery reverse osmosis technology. Before we get into our presentation today, I do have just a couple housekeeping slides to go over with you. First of all, hopefully you should be able to hear me now, but I do want to just mention briefly that should you have any difficulties throughout the presentation today, there are two different ways to connect to the audio. You can connect through the computer or you can call in through a phone line. So should you have any issues today, please feel free to switch back and forth between those two options. And also, due to the large number of attendees on the presentation today, we have gone ahead and muted everyone's lines, but no worries, you can still interact with our speaker today. In terms of interacting with our speaker, you can ask your questions via the questions panel anytime throughout the webinar. And also at the end of the presentation, we do have some time set aside for a question and answer session. So please do feel free to ask any questions that may come to mind, and we will try to get through as many of those questions as time allows. Additionally, we've made available our collection of on-demand webinars that we've conducted over the last few years. You can access more than 50 on-demand webinars over at www.veoliawatertech.com. So please feel free to go over, check out the website, and browse through the variety of different topics to see if any of those may be of interest to you. One other housekeeping note that I have is a PDF participation certificate will be made available to you at the conclusion of the webinar. You should receive that within about 24 hours or so. And one thing that I forgot to mention at the beginning as well, included with this PDF participation certificate, you will receive an email of the presentation. It will be recorded today as well. Also, at the end of today's webinar, you will receive a quick survey requesting your feedback. It should take you no more than 20 to 30 seconds of your time. And for those of you who do complete that survey, you'll be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind as to fill that out for us, we do greatly appreciate any and all feedback. Now, before we hop into the main part of our presentation today, if you're not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider, and we offer our clients a variety of different technologies, services, and project options. And then we also support our clients in a variety of different markets, including various industrial markets as well as municipal markets as well, to help support their water and wastewater needs. So feel free to learn more about us again over at the website www.veoliawatertech.com if you'd like to learn more about us. And now with that, I would like to introduce our speaker for today's presentation. Excuse me. John Corpiel is a principal engineer with Veolia Water Technologies. He has 27 years of experience in industrial water and wastewater treatment. John is a subject matter expert in high recovery reverse osmosis systems and integrated membrane systems, including the associated pre-treatment and post-treatment systems. He is also a co-inventor of 4 Veolia patents in produced water treatment technology. John holds BS and MS degrees in civil and environmental engineering from the University of Pittsburgh and is a licensed professional engineer in Pennsylvania as well as several other states. And with that, I would like to turn it over to John to talk more about us with high recovery reverse osmosis. Welcome, John.
Thank you, Jill, and hello, everyone. Thanks for joining us today. I'm going to talk a little about Veolia's new semi-batch reverse osmosis technology that we call Capsuro, and it's a high recovery RO process. So over the past few decades, freshwater sources have become increasingly scarce throughout the world. At the same time, brine disposal options have become less available and increasingly more expensive due to environmental regulations and sustainability requirements. So these ongoing trends have been drivers for municipalities and industries to utilize high recovery RO processes. So as a result of these industry drivers, Veolia has developed this new steady state semi-batch RO technology called Capsuro, and it's covered by a US patent. We also have another variable volume configuration of Capsuro, which I'll briefly talk about later, and that version is patent pending. So Capsuro is a single stage RO unit, and it consists of an energy recovery device and water buffer tank, and it can operate in either an intermittent production mode, which we typically use, or continuous production mode, as I'll explain in a little more detail later in this webinar. Up to 98% recovery rates are achievable, but we need to look at the specific water chemistry, the source water characteristics, and other process conditions for your given application to validate the achievable recovery rates. So I'm going to briefly discuss a successful field demonstration we did at a power plant in central US that we ran for 14 months between 2020 and 2021. And we actually presented this case study in a paper at the 2022 IDA World Congress last year in Sydney. And then we've also installed our first commercial application at a paper mill in late 2020 in Western US. So Capturo technology can be applied to just about any application that requires reverse osmosis desalination. It's applicable to a wide range of markets, from light industry to heavy industry. This slide shows the possibilities for Capsuro. We've already applied this technology to several of these applications and markets. The sweet spot for Capsuro is for RO desalination applications, which are limited in recovery rates by silica or calcium sulfate scaling potential. Certain salts like silica and calcium sulfate, they don't precipitate immediately. It takes a certain nucleation time for these salts to precipitate. So thus, a semi-batch RO process like Capsuro uses frequent concentrate purging to purge out these concentrated salts from the system before their precipitation induction time is exceeded. Thus, Capsuro leverages induction time to get a higher recovery rate than a conventional RO continuous RO process when dealing with salts like silica and calcium sulfate. So this slide compares conventional steady state RO, which is shown on the top, with Capsuro semi-batch RO shown on the bottom. Now, using a conventional RO to achieve high recovery rates, you really need multiple stages because each stage is limited in its recovery. Generally, you need 3 stages if you want to get more than 82% recovery. And if you want to reach greater than 92% recovery, you actually need probably about 4 stages. So using multiple RO stages, flux balancing can be a challenge. Otherwise, you get too high of a flow out of your first stage and not enough flow out of your final stage. Without adequate flux balancing, the lead elements in the first stage are typically overfluxed, leading to lead element fouling, whereas the tail elements in the final stage have inadequate concentrate flow, leading to a concentration polarization and tail element scaling. Thus, permeate back pressure valves and an interstage boost pump are typically needed for conventional continuous RO systems, as shown in this top schematic. In comparison, looking at this bottom schematic, semi-batch RO processes like Capsuro utilize a single-stage membrane array, and recovery is achieved not in stages, but in time using concentrate recirculation. The use of concentrate recirculation across a single stage improves the flux distribution due to the higher cross-flow velocity utilized, and this improves the fouling and the scaling resistance. Semi-batch RO technology also allows for independent control of the recovery, flux, and cross-flow, enabling flexibility and robustness in the design and operation compared to conventional RO systems. This further enables a more uniform flux distribution, lower energy consumption, and improved operational flexibility. So this shows the 2 modes which Capsuro goes back and forth, alternates continuously between these two steps. On the left, we have the service step, which is where it's producing external permeate. So in this mode, it operates at 100% recovery rate for, say, 85 to 98% of the time. So during this step, the permeate flow rate is equal to the feed flow rate, and all of the concentrate flow is externally recycled, and there's no external concentrate stream during this service step. Now, then after we achieve the recovery target we're trying to get, it then automatically transitions to the purge step, which is shown on the right here, in which we operate at 0% recovery for 2 to 15% of the time. And during this step, all of the permeate is recycled and all of the concentrate is wasted, purged out of the system at a flow rate equal to the feed flow rate. And there's no external permeate during this step. So for example, if we were to operate at 90% recovery, roughly speaking, we'd be running 90% of the time at 100% recovery in the service step, and then we would operate the other 10% of the time at 0% recovery in the purge step. So in this Capsuro operation sequence, the system cycles back and forth between the service step and the purge step all day long. So features of Capsuro, as I said earlier, it has a single stage RO, it uses concentrate recirculation, and it operates in a semi-batch mode, as I described in the previous slide. In this cyclical operation, it automatically alternates between the concentrating step at 100% recovery, which we call the service step, and at 0% recovery at deconcentrating step, which we call the purge step. So this allows us to achieve higher water recovery rates than those possible by conventional RO for applications where you have like silica or calcium salts that would limit the recovery rate of the conventional RO system. So the way it works is it leverages an induction time, as I mentioned earlier. So certain salts like silica and calcium sulfate, they have slow precipitation kinetics. The scale doesn't form right away. So essentially, we purge out these concentrate salts from the system before they have time to foul the membranes. So thus, there's a concentration boundary layer at the surface of the membrane. That's generally where things are more concentrated, and that's generally where the fouling occurs on a membrane. So we frequently disrupt that concentration boundary layer by constantly purging out all the contents from the system during our purge step. So frequently disrupting that concentration boundary layer allows for improved membrane scaling control. So these features that I described offer sustainability with respect to lower energy consumption, waste minimization, and lower chemical consumption, and improved operational flexibility. So these are some of the benefits of operating in a semi-batch RO mode, like as in Capsuro. So this graph, being that we operate between modes of 100% recovery and 0% recovery, as I described, this graph shows how the feed, shown in blue here, and the concentrate shown in red, conductivities increase. They cyclically rise during the service step. So this shows over a 3-hour period, we're operating at 90% recovery, 20 degrees Celsius roughly. So you're seeing 1, 2, 3, 4, 5, 6 cycles here, and you can see how repeatable they are. So during the service step, both the feed and the concentrate conductivity rise, and then during the purge step, it all gets purged out. And I'm showing on the left axis here the raw, feed, and concentrate conductivities, the raw water being what's coming in before we start influencing it by recycling our concentrate. And the permeate showed on the right axis here. You can see it's smaller, but the permeate also too rises and falls proportional to the feed and the concentrate. So this is the same 3-hour period, but now I'm showing pressure versus time, and it acts similarly. As you can imagine, as the salt increases within the system, the feed pressure and the concentrate pressure equally go up, following the osmotic pressure that we're concentrating of the salts. And then when we go to our purge step, the pressure dramatically falls. So this is showing operation up to about 13.5 bar, which is like 200 psi over that same 3-hour period. And this graph, this is from another demonstration we did at another site, and we're running at actually 93% recovery. The recovery shown in black here, and you can see how the recovery increases. And this shows about 4 cycles here. So by the end of the service step, so this red line shows the conductivity corresponding to where we are at 100% silica saturation. So by the end of the service step, silica is supersaturated, as indicated on the graph, because our our concentrate conductivity is above this red line, which corresponds to 100% silica saturation. So even though in this case our service step lasted for 70 to 80 minutes, silica was only supersaturated for this last 10 to 15 minutes, which is less than the nucleation induction time required for silica precipitation. So this system was operated about 160 to 250 psi throughout its production cycle. And this ability to leverage induction time to achieve a higher recovery rate than a conventional steady state RO, it's an advantage of semi-batch RO technology. And this shows a photo of a system that we provided recently at the paper mill. You can see that the parts of the system, you have a cartridge filter, you have a high pressure RO booster pump, you have the vessel array. Here we have 6 8-inch diameter vessels. You have the energy recovery device, which is shown here, which is an isobaric positive displacement energy recovery device. And this particular energy recovery device has an integral energy recovery device with the recirculation pump on one unit. And then we have the water buffer tank, which gives us additional time so we're not cycling back and forth between service and purge step too frequently. And then there's chemical feed systems. They're shown on the other side. You can't see them here. A PLC, and this allows for fully automatic operation, and we can remotely control it and monitor it as well. So this is an example of a CaptuRO skid that we provided. And then we also have a sea container. This is a mobile demonstration plant. It's a 40-foot long sea container that's pretty easy to install. You know, you can take it to a site and crane it in and hook it up pretty easily. And it can, so depending on the application and depending what we're trying to demonstrate, we may operate it anywhere in the 40 to 150 gallon per minute range, but we're basically trying to validate a full scale opportunity and use similar process conditions like similar flux, similar cross flow to see how this resists the fouling nature of a given water we're treating. So this has 6 8-inch diameter vessels, each have 7 elements in there, although we can, if needed, we can use some dummy elements if we don't need all 7. And it's rated for 600 PSI, and it has an automated PLC for remote control and monitoring 24/7 for minimal on-site supervision, and it even has the chemical dosing pumps included. So if you have an application where you feel that CaptuRO could be considered, we could take it to the site and do a validation to understand the application and see how high of a recovery we could sustainably achieve. So this shows a little more detail how the system works. So this is, we normally operate in an intermittent production mode. And this is during the service step when we're actually producing permeate. So you can see in this mode, we have 100 GPM of raw water coming in, and we're getting 100 GPM of permeate, and we're not recycling, we're not wasting any concentrate. So we're at 100% recovery. Now, what happens is the water comes in, goes through the cartridge filter. This valve is closed. This automatic valve is closed. So water goes right to the energy recovery device at the low pressure inlet. And the concentrate, which is at high pressure. So on this schematic, the dark black means high pressure and the lighter lines mean low pressure. So the high pressure concentrate, its energy is transferred to the feed. So you're basically using the high pressure concentrate and converting it down to low pressure while boosting up the pressure of your feed water, and that goes into the membrane system. And in this particular thing, we call per turn. Each turn through the system is at 50% recovery. See, we're feeding 200 GPM and getting 100 GPM, but that's okay because we're recycling all of our concentrate. So we'll go through several turns of this until we finally achieve the recovery we want. I mean, we could get to whatever, if we need to get 92% recovery, that means we have to go through, say, about 12 turns or so of this system, and then we finally get that recovery before we waste our concentrate. So as you can see in the production mode, this valve is open, so we're generating permeate, and water, basically it goes from the high pressure through the concentrate, and it gets reduced down to low pressure, and this low pressure concentrate goes through this water buffer tank and gets recycled back to the booster pump, and that booster pump operates at the permeate flow rates, whereas this concentrate, we can control whatever we want this concentrate recirculation to be. So we have independent control of the concentrate flow from the permeate flow, which is an advantage of the technology. So once we achieve the recovery we need to achieve, which is built into the PLC algorithm, all of a sudden it goes to the purge steps, and all of a sudden this valve closes, and these two valves open. So now all of the water comes, it splits and goes through the booster pump into this energy recovery device. And all of our concentrate now, instead of being recycled like it was in the previous step, it's all purged out. So now we're running at 0% recovery momentarily. We're still running at the same 50% per turn recovery, but in this case, all of our raw water coming in is leaving as concentrate. So we're purging out the salts that we had accumulated over the last service step. So this is operating in intermittent production mode, meaning we don't have any permeates during this step. Now there's another way we can operate called continuous production mode. Now during the service step, it's the same as what I showed you before. We have 100 GPM of raw water coming in and 100 GPM of permeate going out. So then once we achieve our recovery, we go to the purge step. And in this case, notice the permeate is still at 100%, 100 GPM. So we're producing a continuous permeate, but in this mode, that means now we need more raw water feeding. So we basically have to jack up our raw water flow. So this is another way that we could potentially operate in continuous production mode if it suits the needs of your particular application. And then this is an interesting mode that we ended up discovering we could do at a site where the client wasn't giving us a reliable feed source. They had this feed tank to us that a lot of times it would run empty for sometimes. They didn't have good control over the level in their feed tank. So we have this mode where when we get a low level in our feed tank, we can actually close all these valves if we sense that there's too low of a level that is, and we basically operate in an autonomous mode where all of the permeate and all of the concentrate is recirculated, and this avoids an unwanted shutdown flush in the event you have like a low level in your tank. Now, you can only operate in this mode for so long. Otherwise, as you might expect, the water is going to start heating up in the system because we're recycling everything. So the longest we've ever operated in this mode was 90 minutes before going into a shutdown flush. But this just gives you an idea of how you can operate with a little more flexibility if you're not getting a reliable source of raw water coming into you. You can run in this mode on a special basis. Now, this is the demonstration we did at a power plant in the central U.S. So we ran for 14 months. This is that sea container demonstration plant I was showing you that that's available for testing at different sites. So we kept it at this power plant for about 14 months, and we were treating UF pre-treated river water. On average, about 86 GPM average daily permeate flow rate is what we ran at. And over the course of the 14 months, we produced 48 million gallons of high quality boiler feed water, which they actually used at their plant to feed their boiler system. They had some downstream IX downstream of that. But anyway, we ran a side-by-side comparison against their conventional RO, which is there, and our Capsuro outperformed the conventional RO in terms of water recovery, permeate flux, and cleaning interval. And you can see this is a visual of the water we were treating, and this is the feed water. You can see there's some color in the concentrate. I believe the concentrate had about 40 ppm of total organic carbon. There was some probably humic acids in the river water, and we were able to run at a pretty good recovery despite that organic fouling potential. So this just shows the water quality, the range, and the average on silica. So we had to meet permeate quality requirements of total hardness less than 1 and conductivity of less than 50, which we were able to demonstrate. And the scalants and foulants that are of concern to us were barium sulfate, silica, calcium carbonate, and the organics. As I said, there was like 2.2 to 5 ppm of organics in the raw water. So this just compares the performance of the Capsuro versus the conventional RO that was there, which I believe was a two-stage RO system. So we were able to run anywhere from 80 to 93% recovery. 86% was typical versus the conventional RO was only running in the 70 to 75% ranges. It had a lot of cleanings. It had to be cleaned every 1 to 1.5 months. Now you might ask why. It's river water, UF pre-treated, but the UF system they had at this plant, it was not in the best condition. That their hollow fiber membranes were breaking a lot of time, and we're getting a lot of solids coming through due to breakages in the upstream UF hollow fibers. So, but the Capsuro was able to respond much better to those conditions, getting 86% recovery versus the conventional only 74%. And we were running at a slightly higher flux, about 10% higher, 22 LMH versus the conventional was running at 20 LMH. And we were able to get 3.5 to 4 months out of our membranes before we eventually had to do a cleaning, whereas the conventional system was cleaning almost once a month. And we don't have a lot of energy consumption data. We collected a lot on our end, but we didn't have much on their end. But we were getting a little bit better in our energy consumption, maybe 20% lower. And then both systems were, meeting the total hardness and the conductivity. Our conductivity was a little higher on average, probably because we're running at a higher recovery, which, as you know, that the higher you concentrate, you're going to have higher permeate conductivity. So this just shows some references we have. As I mentioned, this is the one I talked about in the past few slides, the field demonstration at the power plant. And then our first full-scale installation, that skid that I showed you earlier in the presentation, was a pulp and paper mill in southwestern US. So that was treating existing primary RO, the concentrate from an existing primary RO for reuse. So we actually ran our rental container there, the C container, for 8 months. And then we installed a permanent skid there in 2021. So that's been operating ever since. So they're operating in the range of 60 to 150 GPM and in the 83 to 90% recovery. And then we've installed some units in Europe recently. One was a dairy industry facility in Belgium, treating dairy process wastewater, operating at 90% recovery. We sold 2 skids there, operating about 110 GPM. That's in the startup phase. It was installed late last year. And then we have a pharmaceutical manufacturing facility in Europe, treating process wastewater for reuse at high recovery. We have one system there running at about 50 gallons per minute, installed in 2022. And then an automotive manufacturing facility in Europe, treating at 86% recovery. There's 2 units there, operating around 60 gallon per minute. And recently, using that field sea container system, we concluded a field demonstration in Mexico earlier this year for a pharmaceutical client, and we were treating brine from an existing primary R that was super saturated in silica for water reuse, and we were achieving over 700 ppm of silica in our concentrate while maintaining reliable performance. So some promising results there. Now, these are some ongoing improvements to semi-batch RO technology that we're leveraging over the other semi-batch RO technologies on the market. One thing that makes us a little different is we're using permeate recycle, and we feel that offers improved fouling and scaling resistance and improved purging performance. Another thing is being that we aren't discharging any permeate when we're running in our purge mode, we're basically running a more stable permeate quality because we're running at a constant flux anytime that we're sending out external permeate. Where if you're dropping your flux, inherently your permeate TDS is going to increase. Another thing, we use this water buffer tank, and that's designed to optimize the cycle time. Because if you don't have enough volume in the system, you're going to cycle back and forth too quickly between production, your service step, and your purge step. So this gives us a better, considering the productivity and the scaling fouling resistance, this optimizes our cycle time. And then, as I showed you in the examples, the ERD-based configuration that we have offers more stable hydraulics and avoids pressure swings, and it gives energy savings. If you don't have that energy recovery device, actually kind of dampens pressure variations and allows for a very smooth operation, we found. And we can operate, as I said, either continuous or constant. We can operate. The raw water feed flow coming in is a relatively constant flow. We can actually keep it pretty relatively constant. So we don't need such a big raw feed water tank compared to some other semi-batch processes. So that minimizes the size of the raw water feed tank. And then another thing, I showed you earlier that low feed tank where we could run in this permeate recycle mode to avoid a shutdown loss, to avoid losses in water recovery. I'll talk about this a little more on the next slide. We have a patent pending variable volume configuration that we have varying volumes of varying quantities of offline external buffer tanks that we can take online and offline to leverage the nucleation induction time by optimizing the cycle time. And then we take a fresh new look at anti-scalant dosing. We do have experience supplying anti-scalant products through our Hydrex line. So we're looking at using that to optimize the anti-scalant dosage within Capsuro. And this shows that patent pending variable volume approach I was telling you about, where during your service step, you start out with all your water buffer tanks online, and then during the service step, you can gradually take water buffer tanks offline to optimize how long you're in your service step. So towards the end of the service step, when things are getting concentrated, you can accelerate that salt concentration increase by reducing the amount of volume you have in your system. So that's something we could potentially leverage. So in summary, CaptuRO is a semi-batch, high recovery reverse osmosis technology, and we feel it's a game changer for industrial and municipal markets, allowing clients to get the highest possible recovery, especially when you're dealing with salts that are slow to precipitate, like silica or calcium sulfate. And it serves a wide range of markets, from food and beverage to chemical to petrochemical, from light to heavy industry. It's a good fit for pretty much all general manufacturing markets. And we have a separate system volume containers to ensure concentrate turn times are optimum. This is our variable volume approach that we're looking at. Enables concentrate salts such as silica and calcium sulfate to be purged from the system before they have time to precipitate, and allows us to run at higher recovery rates while minimizing potential for membrane scaling and fouling. So this really applies to CaptuRO technology in general. And the semi-batch process automatically adapts to changes in salt concentration and effluent, allowing you to run continuously at an optimum recovery rate. So for example, if you have a variable quality or TDS coming in, you can actually set the system to purge at a certain conductivity. So if your conductivity changes coming in, you could set, for example, maybe you want to set your concentrate conductivity to 30,000 microsiemens. So once you hit 30,000 microsiemens, then you go into your purge, and that way you can optimize your recovery for a given process, which is something you can't easily do with a conventional RO system. So that's my presentation. I'll turn it back over to Jill for questions.
Thank you very much for that, John. Very informative presentation. We do have some questions that came in, and as we open up this Q&A session, do want to remind you, if you do have any questions that came to mind as well, feel free to type those in the questions panel. And with that, we will try to get through as many of these as possible. And if we are unable to answer your question today, we will follow up directly with you at the conclusion. So with that, we will kick off our Q&A session. So John, one question that came in here is, compared to a conventional RO design, do you need to run the CaptuRO at a higher cross-flow velocity?
So you don't need to run at a higher cross-flow velocity, but it could be valuable to do so. So depending on the characteristics of the water, generally the higher the fouling potential, it may behoove you to run at a higher cross-flow velocity. So one of the great things about Capsuro is that, unlike conventional RO, you can independently control your cross-flow velocity. So you have a separate recirculation pump that maintains that flow, which is completely independent of the permeate flow. So in a conventional RO system, generally, the higher the recovery you have, that means there's less concentrate flow at your tail end elements of your final stage, which is where the fouling is most likely to occur. Scaling, I should say, is most likely to occur. But with Capsuro, you can have the best of both worlds. By running at a fixed and a higher cross-flow rate, you can keep that high cross-flow rate up, which will minimize fouling potential while also running at a high recovery. So we don't need to run any higher, but depending on the application, like I said, if it's a high silica fouling potential, we're trying to get the higher silica concentrations, we might run at a higher flow, like 25, 30 GPM per vessel. If we're treating a more easier to treat well water, then maybe we could go down to like 15 GPM per vessel. So it gives us a lot of flexibility there.
Great, thanks. Another question is, what type of energy recovery device do you use? And also, is an energy recovery device even needed?
Yeah, so the ones that I showed you in the presentation, we use this positive displacement isobaric energy recovery device, and the ones that we've installed so far, we've had good success using, Danfoss makes a unit called iSave where the recirculation pump is conveniently integral with the energy recovery device. And that was shown in the photograph that I showed earlier. And we've had good success with that energy recovery device. Now, I think as we get to larger applications, build bigger skids in the near future, we could also look at other energy recovery devices as well. We're not stuck on just one supplier. ERI, one thing that they do is they decouple their recirculation pump from the pressure exchangers, and that might be a good fit for some of the larger flow applications. So we're also looking into that. And then there's some applications. So what we find is the energy recovery device, as I mentioned earlier, it really dampens the pressure variations. So that's not so important at the lower TDS range. When you're running at lower pressures, like if you have an application where you're running at low TDS and you're getting like your whatever your recovery rate is, say 90%, you're still only like below 300, 400 PSI. There's not as much of a need for the energy recovery device. And if CapEx is a challenge, then we can offer a version of this. In fact, the versions we offered in those European installations do not have an energy recovery device. They're lower pressure applications, and that's possible, and we can offer that. But where we find where the energy recovery device really comes in value is when you're getting like above 600 psi or 40 bar and higher TDSs above 10,000 as your raw. That's where it really adds a lot of value because you don't have the pressure surges that you would otherwise have if you didn't have an energy recovery device.
Great, thanks. Got a lot of questions coming in regarding the type of membranes that are used. If you can talk
Yes.
a little bit about that.
Yeah, so it really depends on the application. If it's a lower TDS, we'll use a brackish water membrane. On higher TDS, or if we have to meet a pretty low permeate TDS, we'll use seawater membranes. Nowadays we've been using, Veolia has its own line of membranes through the Veolia Water Technologies and Solutions. So they offer a full line of brackish and seawater elements. With that being said, if there's certain applications where for whatever reason our portfolio of membranes cannot meet the application, if it's some kind of like maybe like a certain unusual conditions, we are open-minded to looking at other membranes as well. We've used from other manufacturers in the past, like Hydronautics. So hopefully that answers the question.
Thank you. What is the silica limit concentration that the system could work without any problems?
Yeah, that's you have to kind of look at that on a case-by-case basis. I'll say in general, so you have to understand it uses two things to achieve high silica. One, of course, is the induction time, which I mentioned, but also, we always pretty much always going to use an anti-scalant as well. And as you're aware, I mean, even like a conventional RO system with the right anti-scalant, you could typically, get 150 to 200 ppm silica, even higher, like 240 ppm with the right anti-scalant. Of course, you have to be careful if you have other iron or, metals in the water. It can exacerbate silica scaling. But with Capsuro, the general rule is without doing any piloting, we feel we could do about 15% more concentrated than say a conventional RO is with silica. But in reality, I think we do a lot better than that, and we showed that. But subject to validation via piloting, because as you know, there's a lot of unknowns besides just silica in the water. For example, I mentioned earlier in the presentation, we were piloting this application. It was in Mexico, and we were actually treating the brine from an existing primary RO, and we were actually getting silica up to 650 to 700 ppm. So, but obviously to do that, you need to do piloting to field validation, and that's where, let us know if you have an application. We have that field, that C container that I showed you earlier, and we could validate it to get comfort factor and de-risk the project. So, when you're talking about those levels of concentrations, they definitely need to be piloted. But in general, I would say, if whatever you can do on a conventional RO, we could probably do about 15% more concentrated on CaptuRO, but we have to take a look at your chemistry and your project specifics.
Great, thank you. I apologize. We've got a lot of questions, so I'm trying to get through as many of these that we can. Got a couple application-based, specific application-based for you, John. First one is, could it be used for acid mine drainage? And then a secondary follow-up question on that as well is regarding cooling tower blowdown with high TDS, talking up to even a 15,000 milligrams per liter.
I mean, the answer is it certainly could. So for acid mine drainage, it's typically going to be a very low pH, and typically at those low pHs, you're going to be afforded some resistance to silica fouling as well as calcium sulfate. I mean, it depends what your pH is. So if you're already at very low pH, I would suggest using maybe a different process. In fact, Veolia offers a low pH RO process that's really geared towards acid mine drainage, and that may be a better fit. So if you have an application, let us know. We have a process called AMDRO that runs at like a pH of 3.5 or less, and that provides good scaling resistance against silica and sulfate scales. And so we would have to look at the application. I mean, I'm not going to say no. It's possible that CaptuRO may actually even help to leverage the low pH and do even better. So that's something we would have to look at. But it's possible. But you might want to look at maybe a low pH RO process like Veolia's AMDRO process. Now, for cooling tower blowdown could be tricky because you're really not looking at just the TDS. You have to understand, cooling tower blowdown, they use all kind of chemicals in the cooling water. There's dispersants, there's biocides, there's corrosion inhibitors, and those can be very fouling to RO membranes, especially you got like quaternary amines and stuff like that, and those will foul RO membranes. So you have to be very careful with cooling tower blowdown. I mean, you need the right pretreatment. Yes, a lot of times there is high silica there, and it will leverage that and get you to higher silica levels. But you just have to, some further, investigation and probably piloting would need to be done, and practicing the right pretreatment in front of it may be necessary to avoid fouling due to cooling tower chemicals. Now, the semi-batch operation where we're frequently purging and disrupting the concentration boundary layer would help, but it would have to look at that in detail for the cooling tower blowdown. So if you have an application, reach out to us and we could look at it and lead you to the best solution, whether it's CaptuRO or whether it's CaptuRO with some type of pretreatment in front of it, or whether it's some other technology like say a high pH RO, like we have our Opus line of product, I should say.
Great. Here's another one, a little bit more specific regarding a project, it looks like. They are mentioning that their current feed water has 90 ppm of silica, and can they use this system without scaling? And right now, their recovery is only, unfortunately, at 50%.
So you're doing about a twofold concentration of 50% recovery. So you're taking it from 90 to 180. So yeah, I think this would be something we could look at. Obviously we have to look at what else is in the water. I mean, as you know, it's not just silica. There's likely other potential foulants and scalants in the water that we also need to examine. But I mean, in general, if you're doing at a 50% recovery rate, it sounds like your concentrate is up to about 180 silica. I believe we could do better than that with CaptuRO. I'm sure we could get to at least 240 to probably, maybe closer to 300 ppm silica. But once again, I think we need to take a closer look at the chemistry. So please reach out to us and we'll take a look at your application.
Great, thanks. I think we've got time. We're a little bit over our allotted time, but I think we've got time for maybe one or two more questions here. How do you determine what water recovery is achievable for a given application?
So really, you need to look at your water analysis, the water chemistry, and various, what your temperature is. I mean, there's really what's achievable from a scaling resistance, and as I mentioned, Capsuro adds its most value when you're talking about silica or calcium sulfate limiting the recovery. So, as I said, we could easily do about 15% higher in silica concentration than a conventional RO. And calcium sulfate, that's a little more tricky. Conventional RO is generally limited to about 230% calcium sulfate with antiscalants. We feel we could go a little higher, probably around 400%, pretty easily. But beyond that, we feel we could even do maybe about 600% or 600% calcium sulfate, but you need to do some piloting validation. So to answer the question, we have to look at all the chemistry, not just the scalants, but what are the foulants? Also, what is the TDS, and are we going to be approaching a certain osmotic pressure? So there's a lot of stuff we have to look at, and the application of the anti-scalant in conjunction with Capsuro. So if you send us, if you have a potential application, we can evaluate it and see how high of a recovery rate you can get. And generally speaking, we like to look at a range of, just one water quality sometimes can be misleading. It's good to have, some historical water analyses that were taken at different points in time to appreciate how the fluctuations in the water quality, because generally we're trying to give you a achievable recovery rate that's sustainable, not just a recovery rate that you can get when the membranes are brand new, and then as the membranes age, it goes south from there. So yeah, there's a lot of specifics on the chemistry to optimize that recovery rate.
Great, thanks. I think we've got time for maybe one more here. Just talking in general a little bit, can you talk a little bit more about how we can prevent gradual permanent scaling of membrane elements due to, say, human error or lack of anti-scalants and power failures, and so on?
Yeah, that's a good question. I mean, the scaling resistance, human error could be things like, operators not checking that the pumps are primed, or having a wrong setting on the PLC. I guess you'd have to give me a little more specifics on the human error part of it. I mean, but in general, we do modeling of what anti-scalant dosage we need, and then what we can achieve. We model on paper how high of a recovery we could get it with using Capsuro, to avoid scaling it within our safe zone. But really, you need to kind of, when you're operating, you start to observe, if you're getting, things happening, like you normalize your data. You look at your data every day and see you're starting to get like, if you're familiar with data normalization, your normalized permeate flow is dropping. That's a bad sign. Or your normalized differential pressure is rising. That's another bad sign. Or your salt pass is increasing. I mean, really, you need to kind of look at those things. Those are more chronic problems that, and we can offer systems that monitor those types of things over time. We offer a hub grade line that it looks at the the performance of a system, but other things like power failures, that's certain things like you might need to, if you're worried about that. I mean, that can happen. You have like there's like these emergency mode. I'm losing the word for it. I'm not an electrical guy, but there's uninterruptible power supply, stuff like that you can safely flush during a power failure. I mean, some plants go through that trouble. Others, just deal with it the best they can if power failures aren't that often. But yeah, power failures can be awkward because you're like, especially if you're in the middle of a concentration cycle and all of a sudden the system fails. It's nice to have like emergency power on certain components, like a flush pump that you can flush out the system, for example. So I've seen plants that go through that trouble. Most plants, aren't equipped with such luxuries, and if there is a power failure, you just kind of have to deal with it. But it really comes down to how frequently that's going to happen. I hope I answered the I hope I answered the question.
Great. Thank you so much, John. With that, I do apologize if we did not get to your question. We are about 8 minutes over our allotted time already. But I do want to thank you all very much for attending today. And as I mentioned, if we did not get to your question, we will follow up directly with you after the fact. And with that, I would like to remind you at the conclusion of our webinar today that a short survey will pop up, and we do ask kindly that you will fill that out for us. Should take, as I mentioned, no more than 30 seconds or so of your time. And for those of you that do fill that out, you will be entered into that chance for a drawing for a $25 Amazon gift card. So should you be selected for that, we will follow up directly with you as well. And with that, that concludes our webinar today. And we do thank you very much for spending 45 minutes to 50 minutes of your time with us today. Thank you.
Thanks, everyone.